Hello everyone, we are Hyunwoo Lee, Hayoung Choi, Hyurim Jung, Yu Chan Song from Kangwon Science High School. Today we present an autonomous oil spill collection robot for marine ecosystem protection. The index of our presentation is as follows. Marine oil spills seriously damage coasts and ecosystems, so we developed a robot that uses sensor and hydrophobic foam to quickly find and absorb oil on the sea surface. Seawater has very high conductivity, but crude oil has very low conductivity, so EC sensors can easily distinguish oil from seawater. Crude oil shows strong fluorescence under UV light, while seawater does not, so we can detect and track thin oil films by measuring this fluorescence. A DC motor provides forward thrust, and a servo-controlled rudder changes direction based on sensor data, so the robot can steer along the oil boundary. In gelation, polyols and isocyanates form rattan bonds and a 3D network, creating the base gel from our foam. Surfactants stabilize bubbles made by cyclopentane and make a uniform porous foam, while hydrophobic silica aerogel makes the PEG-based foam hydrophobic and oil-loving. Our surface robot is 35, 30, and 7 cm, has side buoys for floating, oil-absorbing foam at the front, a storage compartment, and sensors plus motors for control. We used two EC sensors, a light sensor, a temperature sensor, a servo, a DC motor, and a 298N driver, and Arduino Uno to build the sensing and driving system. EC values are collected using a temperature sensor, and fluorescence is measured by shining UV light and reading the intensity with TS2591. Simulated oil shows about 0.1 millisiemen per centimeter, and artificial seawater is 11 to 21, giving about a 100-fold conductivity difference for safe and clear detection. We first tested the servo and DC motor separately, then integrated our sensors and the motor driver on the Arduino to complete the circuit. Using data from EC and fluorescence sensors, we made a simple rule-based algorithm so the robot can automatically follow the oil-water boundary. And we set thresholds: both oil, go straight; both seawater, turn left to search; one oil, turn towards that side, enabling simple autonomous navigation. In short, the servo direction is always decided only by the two EC sensors to keep tracking the oil-water boundary. Next, we prepared hydrophobic polyurethane foam from PEG, hydrophobic silica, cyclopentane, and surfactants and TDL, then tested its structure, hydrophobicity, and oil absorption. Next, research results. Using a conductivity threshold of 0.01 millisiemen per centimeter, the robot stably detected and followed the oil-water interface in our experiment. The DC motor gives constant thrust, and the servo turns to about 8 o'clock or 4 o'clock when the left or right sensor detects oil, so the robot follows the boundary. And next, forming failed when we simply replaced PPG with PEG, but increasing isocyanates to a 1 to 1.344 ratio produced stable foam. We found it. And microscope image showed a porous foam with micropores roughly between 362 and 1207 micrometers. And FTIR peaks for NH, CO, CN, and COC confirmed that rattan bonds formed correctly. Discussion is our robot could follow the oil-water boundary using only simple rules, but real seas needs calibration and more advanced control like machine learning. And also, forming with aerosol R972 shows about twice the forming degree, and we planned to measure pore structure, density, forming ratio, contact angle, and oil absorption in detail. In summary, we built a low-cost surface robot that detects and follows the oil-water boundary with EC and fluorescence sensors and simple condition-based control. We also made economical PEG-based hydrophobic foam with aerosol R972 that keeps its porous structure and selectively absorbs oil in seawater. Thank you for listening.